Tell me, I forget. Teach me, I remember. Involve me, and I learn. Hello, everyone. This is Chandrani Ghosh on behalf of Father LeBlond School. Welcomes you to the first module of Hands-on Learning Science. I would like to extend my heartfelt gratitude to everyone for accepting to join this webinar. For those who have joined for the first time, allow me to introduce the host, Father LeBlond School. It's a co-ed boarding and day boarding school affiliated to Council of the Indian School Certificate Examination. Located in the outskirts of Siliguri, a 20 minutes drive from Bagdogra Airport, it offers state-of-the-art facilities for the all-round development of its students. The most time-tested tool in any pedagogical experience is that of maximum involvement of the learner. And there is a valid reason for that. Words are construct of mind, whereas experiences are a construct of heart. For the same purpose, we have our esteemed guests who will enrich us with their experience. It gives me immense pleasure to introduce the octogenarian pioneer, Mr. Samar Bagchi, the science education expert and former director of BITM Kolkata, and Dr. Biren Das, former reader of physics in Vivekananda College, Kolkata. He is a recipient of Lifetime Achievement Award from Indian Association for the Cultivation of Science, Kolkata. Thank you so much, sir, for accepting to grace this occasion. Along with our esteemed guests, we have few students. Let me introduce them. We have Deepayan Roy of class 10 and Somodeep Amin of standard 9. Thank you so much, children. Hope this is going to be an enriching session. After this introductory round, our honored guests shall present their experiments and enlighten us with their valuable knowledge. We will accept questions for our guests from the audience after the completion of their work. We therefore request the audience to text their questions in the chat box. Since we have limited time, we will not be able to take up all the questions. We will accept only few questions for this session. All the other queries will be answered within a day or two through direct messages. Without further ado, let us start with our most beloved young man of 89 years, Mr. Samar Bagchi. Mr. Bagchi is the former director of Birla Industrial and Technological Museum, Kolkata. He is a science educationist, environmental and social reformist. Mr. Bagchi has received the National Award for Popularizing Science through Media in 1996. Mr. Bagchi has conducted more than 300 science workshops with science teachers of school, college, universities across India. He is the mentor of Inspire program run by the DST in universities and colleges. He has conducted the Science Quiz Quest in Doordarshan from 1983 to 1988. We are so blessed to have you, sir. All over to you, sir.
Okay. Good afternoon, everybody. It's a privilege to take part in such a program and especially show when it is organized by Father LeBlond School, where I have been several times, and what a marvelous school it is, what a marvelous setting it is. So I shall take up a topic which is taught from, say, class 7 or class 5, 6 onward, that is magnetism. And this will all be with low cost, no cost experiments. Theory can be read in the book and can be learned in the classroom taught by the teacher. But here, what I shall show you with experiments, the very simple explanations for the different things. Now, let me start with a question to the students who are participating. I have here two iron objects. See, both these two are iron, but one is a magnet, I don't know which one, and the other is an iron. And you have nothing else other only these two. And within 10 seconds, I shall count 1, 2, 3, like that, up to 10 seconds. And you have to tell me how you can find out which one is a magnet and which one is iron. So I shall say start and then start counting. Okay, have you understood? Two iron objects, one is a magnet, the other is iron, but you have nothing else other than only these two, nothing else. So start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Are you ready?
Yes, sir.
Yes, tell me how you will find out. From the fundamental understanding of magnetism, very simple. If you know the property of a magnet, you can tell it immediately. No, you are not sure about it. What you have to do, because time is very short. Time, yes, can you tell me? Yes.
Sir, we will means bring the two objects close together, close to itself. So if the objects attract each other, then we have to check first it will attract or repel. So first it will attract.
No, it can't repel because one is a magnet, one is an iron. There can be no repulsion. Repulsion can only take place if both are magnets. No, I don't think you. Let me show you what you can do. You keep this on the. Now you take one piece and touch it at the center. If it attracts this one, then this one will be iron. This one will be magnet. If it does not, then this one will be magnet and the other one. Let me show you. I touch it at the middle. It attracts. So this one is iron and this is magnet. Now if you touch this one, see this is a magnet. Central portion of a magnet is a neutral region. You touch it here, no attraction. If there is no attraction, it means this is a magnet and this is iron. So simple, so simple. In the middle region of a magnet, there is no attraction. This is called neutral region. Neutral region. Now you see, I sprinkle a little iron filings here. I sprinkle a little iron filings. I sprinkle little iron filings here. Okay, I'm sprinkling iron filings. Okay, now what I do, I take this magnet and touch it here. You see, attraction is at the two ends. Can you show it? Attraction at the two ends. At the center, there is no attraction. At the center, there is no attraction. At the two ends, there is attraction, but at the center, there is no. This is a neutral region. Okay? So with iron filings also, you can show that central portion is called neutral region. Okay, now I shall go over to the next one. Okay. Now, how do I magnetize? That I shall come a little later. Let me show. I have a blade here. There will be a question here also. Biren, this is a blade. Now, I shall magnetize it by a magnet. I shall magnetize it by a magnet. Keep it here. Yes. I keep the blade here, and I have here the magnet, and this shows the North Pole. This shows the North Pole. Now what I start rubbing from here with the North Pole at this end, and then draw it, say, twice. Okay? Now tell me that this has become a magnet now. Tell me, I started with North Pole here. what polarity will be there if it has become a magnet? I shall show you that it has become a magnet. But first tell me which, which polarity will be there if I start with the North Pole and draw it like this. Which polarity will be there?
The south.
South. Okay. He says south. Let me see. Let me see. Put up the fan, please. Now I have here a magnetic needle. I have here a magnetic needle showing north-south. Now I started with north from this side. This is north. So I'm taking this end from which I started north. I started north from this end. So I'm taking that end towards the North Pole. See what happens. Attracted. South Pole is attracted. And North Pole is repelled. South Pole is attracted. And North Pole is repelled. So this will be North Pole and this will be South Pole. This is attracted. So this is South. So this is North Pole. This is South Pole. This is North Pole and this is North Pole. It is repelled and this is attracted. So if you start with the North Pole, this will be North Pole. If you start with the North Pole, this will be North Pole. If you start with the South Pole, I can make it South Pole. I can make it South Pole. Just, I take South Pole now. This is the North Pole. I take the other end now. And just draw. You see what happens. It is repelling the South Pole. It is repelling the South Pole. See again. It is attracting it is repelling the South Pole. So it has become South Pole. If it is a blade, you can easily magnetize it. But in the books, it is shown a bar magnet like this. And with another bar magnet, the book shows it is being magnetized. It will be impossible to magnetize such a huge bar of iron convert it into a magnet just by rubbing it. Now, here in the case of a blade, just once you just rub it, it will become a magnet because it's very thin. Because it's very thin, you can do it very quickly. Okay. Now, you know how you magnetize. I shall show you few figures. One is the single touch method. This is a single touch method. This is a single touch method. This there in the books, you see single touch method. Now, this is the double touch method. How you can magnetize. Okay. Now, now I go over to magnetic induction. Magnetic induction. Now I take a few pins here. Yes, that's it. I am taking some pins. Then I'm taking a magnet. I'm taking a magnet and this is the North Pole. So I'm touching it here. Then I'm touching it here. So this one is attracting the lower one. How it can attract? Unless this has become a magnet, unless the upper one has become a magnet, it cannot attract the lower one. So this magnet has induced magnetism in this. And that induced magnet is attracting this one. Let me see if it can attract any more. Yes, one more. But can it attract one more? No. So 3. Now you see, so this is induced magnetism. Now, I take a very strong magnet. This is neodymium magnet. This is neodymium magnet. On what the strength of the induced magnet is, that I shall show you now. It is attracted here, 1. Now I touch it with this. It's attracted again. Oh my Lord, very strong. Okay, let me. Just 1 second. You see, 4 numbers. 1, 2, 3, 4. So it has induced magnetism here also. Let me see if it can catch one more. So it is catching one more. Can you see it, please? Can you tell me if you can see the experiment?
Yes,
can you
sir.
see the experiment, please? Yeah, you can see the experiment. All right, all right. Because from here I can't see properly. Okay, now you see, is the 5th one also is being tried. So it depends upon induced magnet, depends upon the strength of the magnet. Then you see now, I keep one pin here. I keep one pin here. Then I take this magnet. I take this magnet, take any pole, this side. I'm taking North Pole. I'm gradually taking it. The distance between the two. It's not attracted. It's not attracted. It's not attracted. Not attracted. It will attract now. Yes. So when the distance became very small, then it was attracted. Now you see, I shall try with neodymium magnet. See how it is attracted now. See, the distance is now this much. First it was only this much. Now it is this much. So it depends upon the distance between the magnet and the magnetic substance. On that, the influence of the magnet or the magnetic field is very strong in the case of a neodymium magnet. Okay. Now also it depends upon the medium. It also depends upon the medium. If there is humidity, if there is temperature is high, and all that also will depend the induced magnetism. Now we come to magnetic lines of force. I take a magnet and keep it here. Then I shall sprinkle iron filings. See how the iron filings have to be spread. I can take it. So I am spreading the iron filings all around the magnet. And oh, sorry. This has to be placed below. Okay. No. Let me place it below the board. Let me place it below the board. No. Okay. No. Let me do it. Let me do it. Okay. I shall place it over this, and then I shall take iron filing, then spread it slowly. The magnet is like this. You will see the iron filings are arranging themselves as if in some lines. The influence of the magnet is all round. It's in 3 dimensions, where the magnetic field is there. All around there is a magnetic field. The attraction of the magnet will be there. But I'm showing it only in this plane. How the iron dust are being let me spread it a little more. A little more. Okay. Now these 2 points are the north and south. Now I tap it a little. So the lines of force are considered that it comes out from the north end, goes to the south, and through the body of the magnet, it completes the path. So lines of forces are complete paths starting from the North Pole. It is assumed that it goes to the South Pole, and then through the body of the magnet, the lines of force are completed. So you see how beautifully the iron filings have arranged themselves. Can you see it now? Can you see the iron lines of force? Can you see the lines of force?
Yes, sir.
Okay, please tell me if you can't see it. Now see how beautifully they have arranged themselves. Okay, great. Okay, now please take it out and keep it here. Okay. So now you can also show the lines of force through button magnets, button magnetic compasses. These are very small compasses. See the small ones showing north-south. Now I keep it here, and then I place the magnet. Now this is North Pole, it is attracting the South Pole. This South Pole is here. So from here the distance is quite high. So the impact of North Pole on this small button magnet is much more. So North Pole is attracting the South Pole. So I am placing more now. Now South Pole is attracting the North Pole. You see here, north and south, they are attracting, because it is in between the North and South Pole, so it's parallel to the magnet, So you can draw the lines of force like this. You can take it far. Then also you see, it will be, you can see the lines of force. So lines of force are all around the magnet, the lines of forces are there. Okay. Can you see it now? Okay, now it's all right. All right.
Yes, sir.
All right. Okay, fine. So you can show it by the iron filings. Also, you can show it by the button magnetic compasses. Very cheap. You can get it in the market. Very cheap. Now, I shall show you a figure. You have to let me know by, let me see if it is there. No, I don't find that. Oh, it's there, I think. Let me see. Oh, here. Now, if it is like this, see the figures? What will be the nature of the lines of force in the top case and also in the lower one? 2 types of placement of the magnets are there. One, north and south joined together. In the other case, they are a little apart. what will be the nature of the lines of force, you can find out yourself in your school, and then let me know by mail. You can get my mail from the school. Okay. Next. Now, I shall show you why do we read magnets? Why do we do science? We read science to understand the process of nature, how nature works, and then apply that to make things. As for example, the fan is working because of electricity and magnet. Okay. My watch is there. Watch, if I bring a magnet here, there is an arrangement here inside which does not allow the magnetic lines of force to go there and magnetize the inner parts. Then this watch will be out of order. So I shall show you magnetic screening. Now I have here an iron piece. You have seen that if it is aluminum is not magnetic. It is paramagnetic, but it's not strongly magnetic. Now, if I take a pin, and put it here, it will be attracted by magnetic induction. If I remove the magnet, see, it will fall. Because I have removed the magnet due to which magnetic induction was taking place. Immediately I remove the magnet, that induced magnetism that was formed here, gone. Now I show it again. I raise it, it go. Now I place a iron plate like this. That was aluminum plate, now it's an iron plate. Now iron will be attracted here. Now let me see if it attracts this one. No attraction. But see it at the side. At the side it is attracted. At the side it is attracted. But not at the center. If we take this side, in all the sides it will be attracted. See, it is attracted. Just once again. See, it is attracted. But at the center, there is nothing. This is called magnetic screening. I have shown you that magnet shows magnetic lines of force and their complete path. What is happening? Because of this iron, so the lines of force are coming like this, going inside, coming like this, going inside, coming like this, going in, but it does not pass through. It does not pass through. In the case of aluminium, the magnetic lines of force or the magnetic influence is there below, and it is creating, say, induced magnetism in the pin. But in the case of iron, there is the lines of force doesn't go. But as it is coming like this, or coming like this, or coming like this, so that creates the induced magnetism here in the pins at the side. Okay, so this is magnetic screening, and that kind of arrangement is there in our watches. Magnetic screening is there. Otherwise, inside parts of the watch may get damaged. Okay, so this is magnetic screening. Now, next, I shall show you molecular magnetism. You will read about molecular magnetism in your class. It is assumed, it is not assumed, it is true that every molecule of a magnetic substance is a molecule or atom is a magnet. It's a magnetic dipole. There are north pole and south pole. Now, when you magnetize it, those atomic or molecular magnets, millions, they get adhesed. And this is an analogy of the molecular magnetism. in this test tube, which is a glass test tube, I have kept iron filings, as if each iron filing is a molecule. This is an analogy. This is not real molecule, but it's an analogy. So what I shall do, I shall magnetize it. Oh. I shall keep this needle here. Okay. Now I'm making it haphazard. দেখা যাচ্ছে না তো? দেখা যাচ্ছে না? I'm making it haphazard. Now I'm bringing it near the needle. Both the ends are being attracted. Why? Because this is iron and this is a feeble magnet. So iron and magnet, there will be attraction at both ends. So attraction here, attraction there. Now what I do, I magnetize this. The way I did magnetize the blade. So I shall start with a north pole, So what polarity will be there? If it becomes a magnet, what polarity will be there? Students,
the North
you have
Pole.
seen the North Pole. It will be a North Pole. So let us see what happens to the North Pole here. This is attracted and this is repelled. This is attracted and this you will see it will be repelled. It will be repelled. So I do it once more. Now I again make it haphazard. It is attracted both ends. When it becomes haphazard, when all the molecules, which are molecular magnets, when they become arranged in a haphazard fashion, I will study it in your books how it happens. It is difficult now, and this small time is not there to explain everything. So I'm showing you the experiments, so simple experiments by which you can understand molecular magnetism. Let me try again if it becomes a little better. Let me see. Let me see. If it repels, that means it has become a magnet. Let us see if it repels any of the pole. I do not know which polarity was there. Yeah. Repelled. See, it's repelled. Now here in this case, oh, that's repelled also. Just see, that's repelled. So this is south pole. You see, this is repelled. This is south pole. And I can, now here in this case, you see that attraction repulsion. So this is North Pole and this is North Pole. This is North Pole. What is this? This is North Pole. So I shall take this North Pole towards the North Pole. You see, it's repelled. And if I take it near the South Pole, now when you bring a magnet near a magnetic needle, bring it at right angles to this, and don't take it too near it. Just take it far. See, it is being repelled, and South Pole will be attracted. Now this is a very feeble magnet. This is a strong magnet. See what happens when I bring it too near. I touch it, I hold it and bring it too near. So the North Pole has become South Pole now. The polarity has been changed because this magnet is strong magnet. Has changed the polarity of this magnet now. That has become a South Pole. because this is a very, very feeble magnet. This is a very, very feeble magnet. So if it is a very feeble magnet, then you can change the polarity very easily. Next, let me go over to the next experiment. Then I go to Oester's experiment. Okay. Now this, Mr. Shanyal has to help me in this. Now I have here Mr. Supriyo Sanyal, who is helping me in this work. So I shall request him to help me a little. Okay. So you have to, this is again magnetic compass showing north-south, showing north-south. Now you have to hold it like this. You have to hold it like this. I'm placing this conductor, it is conductor, over the magnetic compass, magnetic needle here of the compass, just over it. And then I shall pass current through this. See what happens to the compass. So my granddaughter will help me in holding it. Hold it here like this, parallel. Yes. Now I shall pass current. This is a battery, and then I shall connect both the ends to the battery and see what happens to that needle. See, the north pole is coming this side. Can you see that? Can you see it? Can you see that the magnetic needle is moving? So this is what found out by which scientist? In which year? This was found out by Hans Christian Ørsted, O-E-R-S-T-E-D, in 1820. He found it out. When there is a current flowing through a conductor, there is a magnetic field around it. See, and now I am placing the where below the needle. See what happens. How the magnetic needle moves. See now, it's going to the other direction. It's going to the other direction. On the right side. On the right side. So when it was on the top, hold it. When it was over this needle, it was going to the left. And when it is below the needle, it is going to the right. Now let me show you by this where. Now I'm holding this. Hold it here. I'm holding it. Now current is passing through this, and a magnetic field is created around it. Now tell me, what will be the nature of the magnetic field? How will be the lines of force in such a case? Because it is creating a magnetic field. Because of that, this magnetic compass, it moved. The needle moved. But this wire was not becoming a magnet. There was a magnetic field created. And the lines of force will be here. On the top, it was like this. At the bottom, it was like this. And we know that lines of force are complete path. I have told you, it starts in the North Pole, comes to the South Pole, to the body of the magnet, it complete path. If it's a complete path, and on the over this where it was in this direction, and below the where it was in this direction. These are parallel lines. How it can complete the path? What will be the nature of the lines of force? It will be concentric circles. Concentric circles. Concentric circles like this. Okay? Concentric circle. So this was found out by Ørsted in 1820.
Yes, sir.
Okay. Now, remove it. Keep it there, please. Keep it there. This is done. Now, let me show you next one. How much time? Huh? Now, I shall show you. Just a minute. Okay. Now, this is a galvanometer. You see, galvanometer is showing near about 0. This 0. Now, this is a coil in which I have taken turns. There are about 30, 40 or 50 turns here. More number of turns is better. Now, I shall show you a very, very important experiment that was done by a person who was a bookbinder. Later on, he became a great scientist, had many scientific discoveries. So, this is a coil connected to this galvanometer at these 2 points. Okay, these are insulated copper wire. Now, what I do, I take a magnet and then keep it inside. Is there any movement in the needle? Is there any movement in the needle? Yes,
Actually,
students.
it is not
Is there any
visible.
movement in the needle? There's no movement. There's no movement. It's stationary. Okay, now you see, I'm moving it. I'm moving it. Do you find the needle moving? Do you find the needle moving or not?
So just bring
Can't
it
you see
little closer. Sir, bring
Can't
it
you see the
little
needle?
closer to the camera. Little closer.
No, so we can't see the
Little closer.
needle.
Camera. Oh, bring it closer.
Just bring it little closer. Yeah.
You can see
Yes,
it now.
sir. It is
Now it is
moving.
better. Yes,
Now
yes.
it's
yes.
moving. That means
Yes,
current is being produced.
Yes, sir. Yes, sir.
Wait, current is being produced.
Yes,
When
sir.
it is stationary,
Yes.
there's no current. So there is magnetic field around this magnet. And when I move it, there's a change in the magnetic field. Whenever there is a change in the magnetic field, then a current is produced here. And that current is being shown by this galvanometer. See it again? And this is Faraday's electromagnetic induction. Electromagnetic induction. No, it দেখা যাচ্ছে না.
Yes, sir. It is
Okay.
visible.
This is all right. So this was found out by Michael Faraday, and due to that, we have electricity, we have fan, and it is there in the generator. And you know that in the thermal power plant, the steam goes, runs a turbine, and turbine is connected to a generator. The generator moves, and it creates current. In the hydraulic stations, the force of the water, the kinetic energy of the force of the water, that moves a turbine like that. In the atomic power plant also, atomic power plants are not good. That's not good because atomic energy is very, very dangerous. So there is a lot of protest all over the world against atomic energy. Okay, so now, so this was found out by the great scientist who became great scientist from a bookbinder, Michael Faraday. There's an institution in London called Royal Institution, and he used to sit at the back. And the director at that time of the Royal Institution, where Jagdish Chandra Bose has also shown his experiments. So in that Royal Institution, he used to sit at the back. But he, when the books used to come to his shop, he used to read it. And while reading it, he got interested. He used to come in the Royal Institution, sit at the back. And then he gradually started working there and then found out a lot of things in science. Okay. Now next. So this is electromagnetic induction, Faraday. Now I shall show you another experiment. For that, this is a aluminum pipe, and you know that aluminum is not a magnetic substance. It is not attracted by magnet. It's a paramagnetic substance. If this magnet is very, very strong, it can attract aluminum. It's a paramagnetic substance. But then this magnet cannot attract it. There's no attraction. Nor this magnet. This is also not that strong. The neodymium magnet which I have is not also that strong. Quite strong, but not that strong to create a attraction to a. Now you see, no attraction. Now I allow this pen to fall, and I shall say go, and you will hear the sound. You will hear the sound. And see how much time it takes. It's nearly instantaneous. Go! Instantaneous. Let me drop it from a a little height. Go! Nearly instantaneous. 9.8 meter per second square is the acceleration due to gravity, my lord. It's going very fast. It's going very fast. Every second it is increasing. The velocity is increasing by 9.8 meter per second. Every second. So you can 9.8 meter means nearly a 3-story building. Nearly 3-story building. Okay, now when I leave this one, it's a pen, dot pen, then it is instantaneous. Now I drop the neodymium magnet. See what happens. I shall say go, then I shall release. Okay. Go. So it takes so much time. Say go. What's happening? Once more.
So why is it happening like that?
No, that I shall come to that. I shall come to that. Now see, go. See, it was taking so much of time. This was found out, but this has been covered by Lenz's law. Lenz's law. Lenz, the scientist, he said that when there is a change of the magnetic flux, this is a conductor, good conductor. Aluminium is a good conductor. All the high tension lines that you see on the roads, those are all aluminium wires. Aluminium wires. So aluminium is a good conductor of electricity, but not better than copper. Copper is much better than that, so far as electricity conduction is concerned. But aluminium is also good. So it's a good conductor of electricity. So when it falls through this pipe, then there is a change of magnetic flux because it's falling. So there is a change of magnetic flux inside this. And when there is a change of magnetic flux, according to Faraday's experiment, there will be current induced in it. That current is called eddy current, will be induced in it. And that eddy current which is induced, that will create a magnetic field. And Lenz says that direction of that current will be such that it will oppose the very cause to which it is due. What is the cause of that current? This is the falling of the conductor, falling of this magnet, because it is falling, so that change is taking place. So it will oppose the cause, that is the falling of the magnet. How it can oppose? So if this is a north pole, then the current that will be produced in anti-clockwise. In this eddy current which will be produced here will be anti-clockwise. If this is anti-clockwise, then a north pole will be created here. So north pole and north pole, this is north pole and north pole here, so that will oppose. So because of that opposition, the fall slows down because this has got gravity, weight. So the opposing force is not that much. So, but then it opposes the falling of this magnet because this current, because of this current, there is a opposing magnetic field which is opposing this magnet. So it slows down. This is Lenz's law. This is Lenz's law. Now, I shall show you. I do not know if it will be successful. Let me see if it works. Now, every magnetic substance, I told you that it has got each molecule or atom is a magnet. Is a magnet. It has got a north pole. It has a dipole. It is a dipole. Each small individual molecule or atom is a dipole. But then its magnetic property of the magnetic substance gets lost if you raise the temperature to a certain degree, depending upon the material. So if it is iron, if you raise the temperature of that iron piece to 770 degrees Celsius, it loses the magnetic property. It becomes a non-magnet. If it is nickel, then it is 1100 degrees Celsius. If it is cobalt, it is small, it is only 360 degrees Celsius. At that temperature, cobalt will become 360 degree, it will become a non-magnetic substance. So this experiment, if it succeeds, it was wonderfully done yesterday when we did it. Now let me first tell you, is it connected? Let me connect it. You see, I have hung, this is a new medium magnet, and this is nichrome wire, which is used in the heater, nichrome wire. This is again new medium magnet, and because this is a magnet and this is again magnetic substance, so it is attracted. Okay. Now I shall pass current in this nichrome wire. Just as in a heater, it becomes red hot. So let me see. It was working yesterday wonderfully, but today when I tried, it was not working. But the arrangement I show you so that you can do it. This is just to fix this wire. This is copper wire. And on that, I have a iron piece, and on that, a small neodymium magnet is attracted. I can open it out. Now I'm touching it. So it is attracted, and then.
So can we focus on this hanging thing so that it is much clearer? Can we just bring it closer? Yeah.
Let me focus it. Okay. Can you see the arrangement now? I do not know whether it will work.
Yes, sir. Better.
Just a minute. Let me adjust it. Okay, let me see. Then I shall heat the coil. This is a magnetic substance, tungsten wire, magnetic substance. When I heat it to its temperature, where it will become a non-magnet, that temperature is called Curie point, C-U-R-I-E, Curie point. So when the temperature of this coil is raised to its Curie point, then it loses its magnetic property. The molecular magnets, they become haphazard in that material, and it loses the magnetic property. Then this will be released. This is attracted by this. If it becomes a non-magnet, now the gravity will pull it down. This is now being pulled here. So if this becomes a non-magnet, it will be pulling, it will come this way. So let me see if it works. এটা একটু বেশি চলে গেছে। Okay, let me see if it works. Okay, let me see. Now I shall put on the switch. Okay. Now I shall send current. Let me see, it will become red hot. Should become red hot. So there is some problem. It was becoming, no, it's not coming. It's not coming. Now you see, it came down. Immediately it became red hot, it came down. Now it will again be attracted. Now I shall pull it again. See. When it becomes red hot, it will be released. Yes, it released. Can you see it? Can you see it?
Yes, sir. Just focus it.
Yes, sir.
Bring it little down. Yeah. That's fine. Fine.
It's
Okay.
not visible.
This is the Curie point. The last there will be question now. Now let us remove this. Please remove it. Open it. Okay. Last one. It will be a question, and you can answer it not now. If you can answer it very quickly, it's all right. Now this is just a weighing balance. This is a weighing balance. and is showing 0. Okay. Now I have here 2 ring magnets in an attractive mode. Both are of the same weight. Weight is 100 each. It's about 200 now. It's about 200 now. It's in the attractive mode. Now what I shall do, I shall keep it in a repulsive mode. So what will happen? It will just float. It will float. Now what I do, I take it out from your view and I place it over this. Can you see it now? No.
Yes, sir. Yes, sir. Yes, sir. Fine,
now,
fine.
Now this is floating. Now tell me, what will be the weight of this now? This is 100. The upper one is also 100, and this is floating. What will be the weight? If you can't say it now, think about it and give me a phone call. Give me a phone call. My phone number, you can get it from Father LeBlond School, and you can write me also in my mail. It is better that you write me in my mail. So with this, I end. With this question, I end my presentation on magnetism. Okay?
One of the viewers, they have written 100 grams, sir. One of the viewers, they have answered 100 grams.
Oh, 100 grams, yes. But I shall not say whether it is right or wrong.
Mr.
But let me say, it's wrong. It's wrong. But you have to tell me, write me why it is wrong. I said, no, let me show you. Let me show you. It is still 200 grams. It is still 200 grams. Then you have to write me why it is 200 grams. Why the weight remains same. You have to think about it and write me by a mail. My mail is very easy, samar.bagchi@yahoo.com. samar.bagchi@yahoo.com. Please send me a mail. Okay. Thank you very much for participation. Thank you very much. Thank you, Father LeBlond School, for giving me this opportunity to again get in touch with this wonderful school that is Father LeBlond. Okay. Bye-bye. Bye-bye. Meet you again.
Thank you so much, sir.
Okay.
Thank you so much for your presentation. It was outstanding, and I think everybody enjoyed. It was indeed a thought-provoking session. And now we will start getting all the responses from the viewers, how they liked it. And although whatever I have seen, it was excellent. Everybody enjoyed.
Okay,
thank you so much, sir.
Thank you.
Sir has infectious energy. We have experienced that. Our children have experienced that. Thank you so much, sir.
Okay.
So next, I would like to welcome Dr. Biren Das. Dr. Biren Das, he is a former reader in physics in Vivekananda College, Kolkata. He is also a guest faculty in Presidency University for postgraduate teaching in crystallography. He is a recipient of Lifetime Achievement Award from Indian Association for the Cultivation of Sciences, Kolkata. Sir is coordinator of physical science at Bose Institute, Kolkata, for organizing workshops for Northeast teachers and students in their outreach programs. At Darjeeling Bose Institute, presently developing an innovative center at Darjeeling. He's a science activist, conducted hundreds of workshops all over India on science popularization and science education for middle and high school teachers. He's a resource person of NCRT and NSTC, JBNSTC, KIIT, UEM, and all the other universities. Over to you, sir. Sir, unmute yourself.
Thank you, Chandrani. It is a great opportunity to meet your students and teachers, because this is a very difficult time we are going on. And it is definitely this COVID situation will not change very drastically so that we can come out on the street or go to the class very frequently. So our option is to learn through this internet, or what we call webinar. Webinar is a new term come, that is through wave we are learning. I will not go very fast. Today I shall perform some experiments on uh, air pressure. Air pressure, everybody knows that we are living on inside air, we are breathing oxygen from air, we are leaving carbon dioxide in the air. And when we are not civilized enough, then what happened? The carbon dioxide we are leaving, that was absorbed by the trees, and they prepare their food from that carbon dioxide and releases oxygen. So there is a wonderful balance between this carbon dioxide emission and the oxygen emission by the trees. So trees and animals, we are also a kind of animal. So we are keeping a balance of this earth. Now gradually with our civilization, we have started using so much energy, and energy being produced, all of you know, nowadays it is a very hot topic. Every students and teachers, they teach, they talk about it, that carbon dioxide emission, methane emission, sulfur dioxide emission has become in such a proportion that our earth is very angry with us. And I have a small theory that whenever there is a very unusual situation on the earth, nature takes some revenge. Either it's a flood, or it is a disaster, some kind of disaster, or some meteorite, very big meteorite falls on it, and there is a huge destruction. Nobody knows why the huge dinosaurs were extinguished from the earth. Definitely there was some reason. There are many reasons given, and students are nowadays from internet, they learn it. There are various reasons. So when we are learning through this wave, then I am not hurrying it. We shall do small experiment, and you will see that all this experiment can be performed because I am using only a glass tumbler. Tumbler means drinking water. We drink water from a glass, we say, but actually right term is tumbler. Tumbler means this kind of, this is a tumbler made of glass, or some plastic pipe, or some plastic bottle. This is my apparatus. And you may think that there are many teachers who teaches in the higher class 11, 12, or maybe in some teachers or some students, they have their elder brothers who are in the MSc. I found that all the students from MSc, from even the PhD students like this, because these experiments, just now we have seen Professor Bagchi's experiment, and Professor Bagchi and myself, we are going around the country, throughout the country. Mostly we go together, and alternatively we do work on the stage. But nowadays stage we have to share it. We cannot do alternatively. Once he is doing, it is our practice that sometimes Professor Bagchi is doing, then I am doing an experiment. I am requesting everybody that most of the experiment here, I will give the answer after waiting few, rather 30 seconds, not much, because it is not that I have to do all the experiments. But thing is that if you see the experiments, how simply it is being done, and what depth of knowledge we can gather from this, that will be very helpful. And everything will be in front of you. So what is meant by this? These are called innovative method, not invention. Inventions are discoveries, and innovations are, the science is known, the theory is known, concept is known, but to teach the students or for learning, if we make certain experiments, that helps you to understand the concept, and you can pass on it to your junior students, or teachers can pass on to the students. So I thought several experiments, but I am thinking that I shall be confined to my air pressure. You can hear my sound, but now I am passing on to another camera where I shall have my, you can see my apparatus. So for that I have passed on. Now I think you can see that there is a tray. Don't bother about this thing. These are just a background so that you can see the glass. You can see the tumbler. The tumbler is here. Now I am simply pouring water in it. You can see that uh, mug through which I am pouring the water. I shall fill it to the brim, completely fill up. Many of you might have seen this experiment, and you see I mean, this is a cover by which we covered a glass where from so that no insects or some dust can fall on it, and I am just taking it on the top of it and drop it. I am not touching. I have not touched it. Now you see, now I hold it and then make it upside down, and you see that it is not falling down. And another aspect you can see that at the center of that, let me remove my hand. No, you cannot see. Okay, let me go to the camera. No, what I can see, you cannot see. Let me see whether
Let's see.
I can.
Yes, sir.
No. What is?
Sir, we can see. Yes.
Now you can see,
Yes,
but
sir.
you cannot see a bubble inside that. That is why I am taking it.
Yes, sir. Visible.
Okay. So the question is, why
Visible.
this cover? I can move it any direction. Doesn't matter. It will remain attached to it. This way, that way, any direction. Now, question is, who is holding this? Because this water is about maybe 250 cc, maybe more than that. If it is 250 cc, then the weight is 250 grams. That means quarter of a kg. Then who is holding it? Now, naturally, I know if I ask you and if you are allowed to unmute and give me the answer, you will be saying that it is because of the atmospheric pressure. As I told you that I shall be giving you the answers, but in a different way. That means you will say that atmospheric pressure is acting through this. Through below. And can you tell me now at this position what I was trying to show you? Can you see a bright spot at the center of the red disk? Very small.
Yes,
Can
sir.
you see it? That is shining. That is because there is a
Yes, sir.
air trapped and the light is reflected from there. So you get a bright spot. And it is actually total internal reflection. But I am not discussing that. Theoretically, you know these things. But anyway, since you can see it, I just mentioned it. Now, there is something wrong when you say that it is because of the atmospheric pressure. Why I am saying so? Before I do this experiment, I take a balloon, very small balloon. This is a very important aspect of science that you must learn it properly in all books. This is the balloon. I am blowing it. I think you can see this. This is a balloon. Now my question is the pressure inside this balloon is equal to the atmospheric pressure or greater than atmospheric pressure or less than atmospheric pressure? If please anyone give the answer on the screen.
So
I will
equals
see.
to.
Equals to. Then why I am blowing? If it is equals to atmospheric pressure, then why there is a tension on this? If I release it, then all around atmospheric pressure is acting. So if I release it, the air goes out. That means outside pressure Should I say outside pressure is more than inside, so that air pressure pushes it and the air goes out? But when I'm blowing, আমি এখন একটা ক্লাস নিচ্ছি, পরে কথা বলবো। When I'm blowing, I am forcing air inside. You cannot keep a balloon like this and expect that balloon will inflate. Now the pressure inside is atmospheric pressure because this mouth is open. Can you see the mouth? This mouth is open and some air is inside.
Yes,
This
sir.
air must be at the atmospheric pressure. Outside air is also at the atmospheric pressure. So if you have to insert air, then you have to push it. So I have pushed air from my mouth, mostly carbon dioxide, inside that balloon, and so natural conclusion is that the inside pressure is more than the atmospheric pressure. So question arises, then how is that when I release my hand, the outside pressure pushes it out if the inside pressure is so high? Who is pushing it down? I give the answer because of the tension of the balloon membrane. It is the tension of the balloon membrane. When you push air inside it, balloon. Now a question is, when you push air inside the balloon, the membrane gets straight. That is why gradually it is very strong, but at the mouth, it is soft. It has something to do. I will discuss it later. This is very soft. All of you know. This part is soft, but this part is comparatively hard. Now my question is very simple. Is the pressure inside the balloon equal or unequal in different places? I want an answer. Somebody should give the answer on writing or anything. Should I cook? Oh.
So equal.
Equal
So
everywhere.
Sir, the viewers are answering equal.
I can see that. Somebody no.
Shikha Mahato is writing different.
That means the pressure is everywhere equal. Now I'm asking, the force acting inside the balloon, are they equal? Because pressure is force per unit area. Pressure is force per unit area. So as there is a pressure everywhere on the wall, there is a force. Are the forces inside the balloon equal or unequal?
So equal.
This is a equal.
Equal.
Yeah, Ashi Guha is writing equal. Most of them are
Okay.
writing equal, but one of them they said different. Equal. Aparna Shah is writing equal.
Aparna Shah is writing equal. But let me tell you where the force is acting. Is it acting in the mass of the air or on the surface of the balloon? Because in the mass of the air, I am just imaginary thing I am observing. There is a area inside the balloon. So from this part, air pressure is acting. From this part, air pressure is acting. So the total force on both the sides are equal. So inside, you cannot detect any force, but there will be force everywhere on the surface. That means if we consider this is a surface, then this is a surface, then the pressure is acting, so-called pressure is acting. Man, I am very much in objection to that, but we always say pressure is acting in the upward direction on the surface. And below here, if we consider another area, pressure from inside it is acting. So forces are acting in different directions. So naturally, you will have to accept that the direction of the forces are different inside the balloon. Though the pressure inside is uniformly equal, but because force is a directed quantity on the surface, they are equal. Let me draw a figure that will that might give you some idea. But quickly, if I can find out some sketch pen. but it is not near me. So anyway, so I cannot talk in space, but let me show you that this balloon has forces acting on its surface all over. Now, if I release this, I am looking at, if I release this, in which direction will go? I am holding it from the top. So your answer will be, it will go down. Why it will go down? Who is forcing it? If I hold it in any direction, let me make it bigger. If force is acting from all direction, then you see I am putting this plate and releasing the balloon. You see the balloon is not moving away from this surface. Again I am doing the same thing. I am putting my hand here and see it is attached to my hand. If I put my hand on the top, I am holding this and put my hand on the top. Put my hand on the top, then release. You see, the balloon is attached to my hand. That means the inflated balloon has forces on this surface, on this surface, on this surface, from on this surface, everywhere it is acting outwardly. So when I'm holding it here and release this air from here, the force which is acting in this area vanishes. And therefore only force remains is at the back of the balloon, which is pushing it towards it. So when I put my hand here, balloon will remain on my hand. That means it is the force which is forcing the balloon. Pressure is uniform all over the balloon, but we should use a term which is called force due to pressure, because pressure is a scalar quantity. You cannot say the pressure is acting this direction, pressure is acting that direction, though we always very loosely say that thing. But here again I come back to my experiment, that it is this is not falling because there is an upward force because of air pressure. I hope you understand. Somebody say yes or no.
Yes, sir.
That right.
Yes,
The
sir.
pressure which is acting here multiplied by this area is the total force acting on it. And so the weight of this glass, I mean the water inside this tumbler, that must be equal to the force due to air pressure, and that is why it is holding. Now, if I put some very, I mean, heavy, I mean, comparatively heavy coaster, I am using another coaster. This coaster is, again, it is placed either on the top of the glass or bottom of the glass. This is a coaster. Now I also turn it upside down. I don't know whether it will fall down because it is very heavy. It is not falling, but some water is coming out, and you can see some water has gone out, and still I do not have to hold it. I can turn it over. Now if I slowly move it, you see the coaster is moving. It is very loosely connected to the glass. If I give little pressure, and yet there is some air also there, some air has gone inside, and this air has some pressure and force due to some pressure. The weight of the glass is giving some pressure below, and the atmospheric pressure giving a force in the upward direction. Force due to atmospheric pressure is in the upward direction, it is holding. Now see, I have shaked it, so it has fallen. Doesn't matter. But thing is that when it is holding, see, when it is holding, It is quite heavy, but if I take some other material, it will hold, no problem. This is very light. You see, it is holding. No water is here, but still it is holding. And from the side, you can see some shining part. That means it is some water is there. If I make it dry, I'm pushing it on a handkerchief. Now it is dry, and also I make the glass dry. See, it is not attaching because the water molecule is not here. So the force due to water molecule, which is called adhesive force with glass and water with this plastic, that has little part to play, very little part. This is because of the molecular force. This is because of the molecular force. But when it is filled up with water, partially filled up with water, and I put this coaster here, and I told you that this is moving. Now a question arises. Is the pressure inside this? The air is here. I am just taking out this coaster. Air inside. When I close this, what will be the pressure inside the glass? Why I am going in so details that if there any student or teachers, they will understand that when you do some experiment, you must be very thorough with the experiment. What are the things happening? So I'm asking, what is the pressure over here? Is it atmospheric pressure or less than or greater than? Give me some answer, one or two, anybody.
So equals to the atmospheric pressure.
Equal to the, very good. Oh, it is you, because you know the answer. We have discussed it earlier. Anyway, it is equal. Why it is equal? Because when at this temperature, and this is a particular volume of air within the tumbler, temperature, pressure, and volume, they are remaining same. When it is open, the tumbler volume is same as that when it is closed. So inside pressure is equal to the atmospheric pressure. So now the question is, if it is atmospheric pressure, and if I turn it over, anyway, I take a lighter one. This is too heavy for this. Little water I take. This is a comparatively lighter one. It will not fall. Now, if this is at atmospheric pressure, water has some weight, and this is also atmospheric pressure. So the force acting on this, because the area of the tumbler, mouth of the tumbler is same inside and outside. So the force due to air pressure is same, which is acting from the downward. So you have to accept that if it is in equilibrium, then something is different in this case. Something is different. What is that difference? I do it another experiment. I have a very special type of glass. This glass has a hole below. Can you see the hole? Water is coming out. So
Yes,
I
sir.
close the hole. I close the hole. Then I place this water. Let me put some more water. Water is coming out very quickly. I close it. Now it is like ordinary glass. I am putting this coaster on the top of it and holding this below. I am just turning it over. Now I release my hand. It is not falling. You can see that I am holding my finger on the hole. So it becomes an ordinary tumbler of plastic. So the coaster is also holding there. Now, if I release my finger, what will happen? Very simple question. Now you know what will be the answer. I know everybody knows that as soon as I release my finger, it will fall. It will fall. What does it mean? Since there is a hole, the air inside, whatever air has inside, when I take it upside down, whatever air is there, this pressure is less than the atmospheric pressure. As it is in equilibrium, the upward force must be equal to the downward force. Doing some experiment, you must conclude if there is no motion, everything is stable and in equilibrium, then definitely this downward force is equal to the upward. Acha, what happened? Now you understand this is moving because weight of the water pushes it down little bit. Let me take some more water, then you will see. I have taken a tray so that all the water goes inside that tray. Otherwise, the whole area would have been flooded. So I take it upside down. When I release it, this weight of the water pushes this plate down. When it pushes it down, then what happens? A small layer of water is there. And when it goes down, then what happens? If this layer, I mean this coaster goes down, then this level also goes down. That means this volume become more. Previous whatever volume it has, but now the volume has increased, maybe very slightly. But that very slight amount of increase in the volume make this pressure less. So when the pressure is less, this pressure plus pressure due to this water and the weight of the coaster all become equal to this. So by that we can show that means the inside pressure has decreased. That is why it is holding. Whatever may be the water, it may be completely filled. And one thing I should discuss with you, in this case, if I turn it over, it will fall down. You see? But it has not fallen. Anyway, most of the time it will fall, but in this case, now you can cheat your student. How? When you put this plastic over it or a card, what you can do after inverting, you can push it. So when you push it, some water will come out. Now it will very strongly attach to this, you see. So you can make tricks, you can make them, I mean magicians make tricks to fool them, but scientists do experiment to make you understand, thoroughly make you understand. If I push it, what happens? The inside pressure goes down, so it will definitely hold it. But normally it will hold. Now I will pass on to a same experiment in a different way. Now let me take. You can see there is a cover for this glass, and there is another container. I am attaching this container to it because I want to show that the force which is acting from inside, that may change. That means total force which is acting, that may change. Now you can see this. You can see it is like a balance, but it is not a balance. What I am going to do, I am going to pour water on this. I can make it full or little less. It is little less. You can see it is not completely filled. Now I put it on here. Now I make it upside down, but this length is too long. If I release my hand, you see it is, I am holding the glass tumbler only, and it is hanging. Now I have certain coins in my hand. I have certain coins. Again I am showing, you can see the glass which is not completely filled and there is a cover. I am holding on the top, so I am going up, and then what I am doing, I am adding some coins in this. So the weight is rising. So therefore the inside force has to rise in the upward direction. I mean that if the weight increases, that means inside there is a downward force. Here also I am giving 1, 2, 3, 4, 5, 6. Each coin is 5 grams. 7, 8, 9, 10, 11, 12. So I took 12 coins, and when it is 12 coins, that means 12 into 5, 60 gram weight I have put, but still it is not falling. It is a very nice fun if you do it by yourself, that how much this thing can take up. So you can do an experiment in a repeatedly in a different way, so that you get some understanding that it is a continuously changing situation. What is changing situation? That when you are putting weight, it is gradually going down with a very small amount, So it is gradually going down and down. I am exaggerating the figure. And so it is adjusting. That the pressure inside the air is gradually decreasing so that it can hold it. But after a certain limit, but you have to be very carefully do the experiment. You can try it at your home. So many of you might have seen this kind of experiment with glass and water, but I think this is something very, very nice which you shall see. Now you see there is a molecular force. We have discussed there is a molecular force. That means between the glass and water, there is a molecular, so it is holding. This is the molecular force. No water inside, so this is the molecular force. Now let us see how much. It is a. I just leave it down somewhere. I also put it down, and then what I will do, I will pour this water so that I can do the experiment. So I poured this water. Lots of water in this trough. Now it is free from water. I take this, but now I need this thing, and I put a plastic on it. What I do, first I fill up the glass with water, then place it on this. Oh, sorry. I hope you can see the situation. There is a plastic plate, and this is the glass full of water. Now what I do, let me now what I'm doing, I'm taking the same coins. These are the coins, and I'm placing this coin below this. Very slowly, one after another, 120-degree apart, I am placing them. And the third coin I am placing here. Oh, it is 2 coins I have taken. So I take 1 coin out. Now you see no change in water level. 1 coin is here, 1 coin is here, 1 coin is here. And if you measure this thickness of this coin, then you can easily see that each coin is of thickness of 1.5 millimeter. That means now the separation between this plate and the tumbler edge is 1.5. Now I put more coin on the top of each. So I take 3 more coin, and very slowly I put this. 1 coin here, 1 coin here, and another coin here. Now certainly we have seen a drop has gone up. Why a drop has gone up? Because when water, you have some water in between, then that water has to come from the glass. So some water has gone down to fill up the space. Still no water is coming out. So again I put 3 coins on the top of it. Now the height is 3 millimeter. So now I put another coin, so it will be 4.5 millimeter. But very carefully, without shaking hand, you have to do it very carefully. You have to have a very. You can do the experiment at home because everything is available at your home. So now it is 4.5 millimeter. Who is holding it? It is the. I will talk it later. Now I have 3 more coins. Let me put it on that. Now, let me tell you, I have almost reached the limiting case. The weight of the water is held by water itself. That means surrounding the tumbler, whatever is there, whatever water is that water surface is holding it. So again I put the 4th one. That means it will be 6 millimeter height. Very carefully, if my hand shakes, then the entire experiment will go bad. Now it is 6 millimeter height, and you can see water is coming out. I am happy that only about 3/4 inch water has come down. You can see this much water has come down, and let me have something to point out that here everywhere is water. I can take out this water with the help of a syringe or something like that, and it is still holding. With the help of syringe, so I cannot take much of water out, so it is protesting. Now I need something else. What I need something. Some liquid should be there. I brought it, but I don't know where I kept it. Sorry, I could not find it. This is the problem with me. But I can brought it from my home. Just you wait for a few 1 minute. So I am back. So I am back. You can hear me. I am put my speaker on my button.
Yes, sir. Yeah.
Now I have something in my hand. So I just sprinkle it there. So can you recognize what is this?
Yes,
I think
detergent.
the girls will be able to recognize this. What is this?
Washing soap. Yeah. Dishwasher.
Washing soap.
Yeah.
This is dishwasher, Vim job. So
Ah.
I put little soap on the water. And you can see the spectrum also. Inside there is a lot of color. You cannot see from the camera because camera doesn't efficient to hold this. But what happened? Why the water has fallen down? And you can see the gap. I am putting this. Can you see the gap between the coins?
Yes, sir.
The glass.
Yes, sir. Yes, sir. Yes, sir.
You see, so much gap was there. That means this is because of the surface tension of water.
Yes.
This is because of surface tension of water. The water is holding it. And when I put soap solution, the surface tension of the water decreases. So when the surface tension decreases, naturally it cannot hold the weight of the water. So water has fallen down. So you see only one experiment, how much water a tumbler can hold when a card is. I have extended so many things on this part. So it is very interesting that instead of doing lot of experiment, it is better that you do only one or two to give you some interesting phenomena, to make understand interesting phenomena. Now I will pass on to now this is also a very famous experiment which I am going to do. This is a candle put on a plate, on a tea saucer. This is a tea saucer. Now I have a glass. This is specially, I mean, I have designed it. You can see it is graduated. This glass is available almost in all the schools. This is borosilicate glass, very thin and good quality, but this is cylindrical. So when I place it, I put some water here, and when I shall place it on it, what will happen? Let me put some water. Now you have to predict what will happen. No fire. I am putting some colored water. Now I am going to place the glass on it. No fire is there. Some of you might have seen this experiment, maybe Praloy has seen it earlier. But now I am going to place it. Will there be any change in the level? I mean, inside this glass, when the glass will touch the level, whether there will be, I mean, whether the inside level and outside level will be same, or inside level will go up, or the inside level will go down, what will happen? Predict. Give me some answer. Somo, sit calmly for a few minutes. Okay. Nobody is giving some answer. What will happen? Whether the level will go up or down. I am trying to. Can you hear me clearly? Chandani ma'am, can you hear me?
Sir, yes, sir. Yes, sir. Clearly, I can hear you.
Nobody is responding. What is happening? It is
No,
very
no, no. One
easy.
of the children, children are facing some network problem.
Oh, acha, acha. Then let me show it what happens. Let me show it. I am just simply pasting it. So normal answer will be the level will be
I think it
equal
will
or
go
the
up.
level will go up.
Yes, sir. The level will go up.
The-
Tishita Roy Chaudhary,
go up.
Sumaira Ashraf, all of them
Now
are
you
writing
see
it will
what
go
I-
up.
Now you see it is go down. It has gone down. Can you see the plate? You can see the plate is visible now.
Yes.
So you see, before doing an experiment, I have another experiment to show you that when you place the glass, the level of water inside the glass goes down. Why? Very simple. Because we are dealing with atmospheric pressure. When the glass touches the surface, it encloses an amount of air inside the tumbler. So inside the tumbler, whatever air is there, it is enclosed or it is closed by the surface. Now when you go down, the water will try to go up. But you see, the atmospheric force, force due to atmospheric pressure is much more. So what happens when the water tries to push the volume of air inside? What happens? The air pushes the water outside. So when I shall burn this candle, your answer I know. When I burn this candle, water will come up, but how much I don't know. But there is I mean, you can understand whatever it will come up, it has to be taken account from below, because all the water has gone out and you can clearly see the bottom of the plate. Now I am taking it away. This has also very interesting turn points. So be careful what I am doing. Let me take a match. I know my fan is moving. I don't know whether I should be able to. Let me switch off the fan. Let me switch off the fan. Sorry, students. দেখা যাচ্ছে আমি ওটা করিনি, ওটা যদি আমি এক্ষুনি খুলে দিই তোমাকে দেখা এখানে আছে, এই ক্যামেরাটা এখানে একদম সোজা তোমাকে দেখা শোনো না কথা, আমার কথা আবার শোনা যাবে। Now now the candle is burning and I am going to put the tumbler on the top of it. You see, I put the tumbler on the top of it. No water is coming inside now. You can see the plate, no water is coming out. So long it will be burning, now water is coming out. How much water has come? Almost the height is 2 centimeter. Almost the height is 2 centimeter. Let me rotate it so that you can see the reading. It is 2 centimeter. Here it is 2 centimeter. Now again I do the same experiment. Same experiment. What I am doing, I am cutting the candle by little. It is difficult, but I can make some arrangement. How can I make it? I have certain things to fix. So as an experimenter, you must know what are the things you can do. So when you do experiment, I have just taken some clay and put it there, and I again the candle should, it is because it is weight, it is taking some time. The candle is weight. It is diffusing, now it is burning. Now I put it again. Same experiment I am repeating. It is almost 2 centimeter, almost 2 centimeter. Now again I am putting fire to that. Let it burn for a while, just little bit, or I can put a little bit of paper so that the burning is faster. What is the difference now? You cannot see because the camera has a limitation, but to show, I think if I can make a obstruction to this, how can I make an obstruction? Can you see the flame is little larger? You cannot see this, but when I put this,
Yes.
You can see the flame.
Yes, sir.
It's very large.
Yes, sir. Yeah.
Now put it. I am putting the same glass on it. Now we shall be seeing how much water will rise. It is 2.5 centimeter. That means, in fact, it is trying to take some water, air from outside. It has more than 2.5. I can put a lens here. I had a lens, but I don't know where I put it. I couldn't find the lens. Anyway, I had a big lens, but I don't know where I kept it. Anyway, you have to take my, it is almost 3 centimeter. It is more than 2.5. Why this difference? Now you see, if I take another plate, which has 3 candles, it has 3 candles. Now if I put fire to all of them, this is the first one, second one, and the third one. Now again, I am repeating the same experiment. Let me show you how the flames are there. Can you see the flames? There are 3 flames.
Yes, sir.
Yes, sir.
Now a lot of air is going inside. So it is more than 3 centimeter. Now what is the reason? That this tumbler has the same volume. This tumbler has the same volume. It has by height it is 11 centimeter. From below, if you count, this is 1 to 11 centimeter. So height of this 11 centimeter. So whatever air inside this, it is fixed. But when there is one candle, the height is something like less than 2 centimeter. When I cut the top of the thread, then when it is burning much, then it is 2 centimeter. Now when there is 3 candles, it has gone to 3 centimeters up. Why these are the difference? In this tumbler, there must be same amount of oxygen. Because this experiment was, 1 minute, Chandrani ma'am, it is now 1:53.
Yes.
Should I
Yes, sir. No, if you have planned something, then
there are lots of experiments. But I am trying not to do all the experiments, but I am trying to make them understand what is happening.
Yes, sir.
So that is why if the students are interested, then I can continue. Let me finish this one, why it is happening.
Let us finish this and then we will catch up next time.
Now, there are much more experiments till now. We are talking about atmospheric pressure. Obviously, one thing is that when different amount is rising, it should, we know the oxygen is 1/5, approximately 20% if I take. 20% of 11 centimeter, if I take 10, then 20% is 1. If it is 10, then 20% is 2 centimeter. So initially 2 centimeter is the right answer. But when there is 3 candle, it has gone up to 3 centimeters. So it shows that the oxygen content is more, but it cannot be more. It cannot be more because for the same volume of air, it cannot have more oxygen because the same composition is everywhere. So why it goes up? Naturally, if you see what I am doing in 3 cases, one case I cut that I mean this whatever it says, the
Wick. We
wick.
have cut the wick.
Thank you
Yeah.
very much. Thank you very much. The wick. Then size of the wick is small. So when I burn it, it produces a very small flame, and that small flame produces less heat. When it is a normal wick, then the flame is larger. So it is producing more heat. And when there are 3 candles, it is producing more heat. That means 3 candles can produce 3 times heat. That means by this experiment, we cannot measure the percentage of oxygen in air. But what it does, when I am putting this glass on it, what happens? These flames make this air hotter. So the hot air goes out of the glass. So actually the quantity of air decreases, and that is why more air and more water goes inside that. How we can determine that? So we can do an experiment. Let me remove 2 of them. I am removing 2 of these candles. Let be there one only, and I am taking a bottle, plastic bottle. What I am doing, I am putting fire on it. I have removed 2 candles, only 1 candle is there. Whether air is going out, you can see it now. You can see it now. I am putting this candle, this bottle, you can see the bottle, and put the candle inside. I just go inside. Now you see the bubbles. Can you see the bubbles? A lot of bubbles has gone out. Now the candle
Yes,
has
sir.
gone out. Now you see what will happen. So you see what happens, that because hot air goes out, that is why there is a less amount of air. So when it is cooling down, this less air get contracts, and therefore water goes inside. So this experiment proves beyond doubt that air expands. This experiment shows that because of the candle, the air expands and some air goes out, and therefore the water goes inside it. So this is not an experiment to show the so we are really now is your student eager to continue? Then I can continue, because
So you can
small
finish this
experiment.
principle what you are showing. Yeah. Whatever you are showing now, the principle that we are working on.
Everything
Otherwise, we
are
will catch up in the next episode that we are.
okay, fine. Let me put this. Now we have heard about Magdeburg's hemisphere experiment. What is Magdeburg's hemisphere experiment? Oh, I have to put it because you can see the hole. I covered it. There is no hole because that is an optics experiment. Anyway, Magdeburg's hemisphere experiment. What is that Magdeburg's experiment? What is Magdeburg's experiment? That there are 2 hemispheres and there is a 2 rings on the 2 sides. In the book, there is a picture that 7 horses are connected to this side, connected to this side. First thing, let me tell you, Magdeburg's hemisphere experiment is not in the name of the scientist who have done it. Magdeburg is a small village, and the name of that village is Magdeburg. Since the experiment was done in that village, because they have used 14 horses to open that, the big sphere, I mean this spherical ball which is cut at the center, they can fit very easily together, and but it is absolutely airproof. and when the air is taken out with the help of pump, 7 horses is attached one side and 7 horses attached the other side, and when the horses try to open it, they cannot open it. But for that experiment, you cannot have 14 horses in your school. What you can do, you can take something like this. You can see these are called vacuum cups. This is used in the dining hall. The glass top is being kept there.
Yes, sir.
Now
Rubber
these two,
suckers.
this is vacuum cups. So what I do, I just place lightly over here. Now if I pull it, then it is not attaching. But if I just press it little bit, now the shape is like this. Can you see the shape? Let me
Yes, sir.
see if you can see. Now you can see the shape. I have pressed it from the two sides. Now
Yes,
what I
sir.
am doing, I am trying to open it by just holding this buttons. I am trying to open it. I cannot open this. I cannot open this. This is a small thing which is about 2 inches diameter, less than 2 inches diameter. But when I press it, I cannot open it. Why it is so? Because the force due to atmospheric pressure is pressing it. When I have pressed, all the air has gone out. When I am trying to open this, whatever air inside that expands, so the pressure goes down still. So it cannot be opened, and I can tell you that I had an experiment to measure air pressure. From that, we can find out that air pressure is 1 kg per square centimeter. That means if we consider that diameter of this is about 1, 2, 3, 4 centimeter, that means pi r square, that means 16 into 3, that is about 50 square meter per centimeter. That means it can hold 50 kg. So it is not possible. Maybe my calculation is wrong. I have very hurriedly done it. Maybe 3 centimeter. Of course, it will be 3 centimeter. You can see this is 3 centimeter. So 9 into 3, it will be 27. So at least 27 kg force is necessary. That means if you hang it from the ceiling, you need 27 kg to open it. So my power is not enough to open it. But if you allow this to some air to go inside, by putting your nail, then it will be very easily open. Now last experiment I am going to, now it has opened. So this is an alternative of the Magdeburg hemisphere experiment. Now I am going a last experiment, because I have so many experiments. It is very difficult to complete them very easily. And now I am going back to my camera. Yes. This is the structure of my apparatus. This is a bottle. I can open this bottle. This is a bottle, and from the bottom, a pipe has come up and it has gone here, and it is just putting like this. What I am doing, I can put it here so that you can see the entire thing together. How I just little rotate it. I hope you can see the entire element now. I am pouring.
Yes, sir. The bottle is visible, but I
Yes,
think
sir.
if we go little back, I think it will be much. The
No.
camera can go little back so that we can see the entire thing.
There is no
If it is
space to
possible.
make it.
Fine, no problem. Otherwise, it is available. Yeah, we can see it. Yeah, sir, fine.
It is almost totally visible.
Yes, sir. Yes.
Now I am pouring water. Most of my experiment today is water, because it is a very easily available material. because on the same table I put my computer and put a guard on that so that the water does not go to my computer laptop. Now it is completely filled up with water. And I am holding it because the water is at the top of it, and here also water is at the same level. You know, the equality of the liquid level in if it is connected. So here and here it is like a U-tube. Now what I'm doing, I'm just let the pipe go down and see what happens. You see, the water is coming down, though the pipe has gone up. The pipe has gone up, but the water is continuously coming down. You can see the water is coming down. And the level of the water in the bottle is also decreasing.
Yes.
Now you see the water is going up and coming through this tube. I mean, it has gone up to this. Then it is coming here and it is falling. And the water is continuously going down. How it is happening? It is a very interesting experiment. See, the water is going down, and from below the water is goes up, almost at the top of it, and water is falling here. What is the principle involved in it? Please think, student, think. It is a very interesting property of
So
the
I think so the
uh,
atmospheric pressure is putting pressure on the water, because
but
of which
here
it
also
is
atmospheric pressure is
the
there.
water is coming out.
Why the atmospheric pressure? What is this principle? This is a very common principle. I will show it now. See, continuously it is going. Let me leave it like that. I have another bottle. It has a bent tube. Can you see the bent tube? Yeah, you can see it.
Yes, sir.
Oh, you can see it. You can see the bent tube on the screen. Now, this is, I can put it here and I cork it up. Now, I am going to pour water in it. So, I have a bucket of water here. So, I am putting this. Water is up to this, but no water is coming out because below it is open. Below it is open. Now, as soon as I come to the top, see, the water is falling. This is principle of siphon. This is, I mean, whenever we see in the book, now it will not fall because the open end has come here. This is also principle of siphon. Here the tube is inside. I kept this tube outside. Why it is falling? Why it is not resisting? For that I have another experiment, very small experiment. It will not take much time. I have two test tubes. If I turn it over, what will happen? The inner tube will fall down because of the gravity. Now I pour some water here. I am putting my colored water. Now I put it here. Because of the weight of the inner tube is much more, it is going down. Now I take it up and release it. See, it is going up. It is going up. Again I am doing it. I poured the water. Put this here, because of the weight it is going down. Now I am just taking it, and you see it is going up. Anti-gravity test tube. Why it is going up? because when the water is coming out from the aperture here, coming out from this little gap is there, then there is a vacuum here, and nature does not allow any vacuum. So what happens, as soon as water comes out, the atmospheric pressure pushes it up. The same principle as applied is here, because the siphon, in case of siphon, what happens, if I take this, when I am pouring water, the water gradually goes up in this, and since this is open, water is also going up through this, and so long it will be below this, so long it will be below this, it will not come out, because this is atmospheric pressure, this is also atmospheric pressure. But as soon as this water comes over here, it starts falling, and as soon as it starts falling, this is filled up of water, and this is also gradually filling up with water. So there is a vacuum, partial vacuum created here, and that pushes the water continuously. The atmospheric pressure is pushing the water to go through it and come out through this. Same thing is happening here. When I put this here, the water level is same to this place. When I put it down, then what happened, that some water, as soon as it starts falling, then this is a low pressure area. Oh, sorry, you cannot see it. This point, when water come to this point and started falling this, then because of the gravity it is falling, there is a low pressure at this point. So the atmospheric pressure through this neck of the bottle is pushing it, so the water is continuously coming out, and it is looking like a swan. You see, this is a beautiful design. It is looking like a swan. You can make a swan shade here, and this is his or her tail, swan's tail. So it is a very nice experiment and looking beautiful for this. I think there are many more experiments, but it is already 2 hours 12 minutes, so I should finish. Chandrani, thank you very much for giving me this opportunity. But as I said, I just thought not to do many experiments, but to give some glimpses of innovative experiments which can inspire the students to the experiment by themselves. I have not used anything which is expensive. Rather, everything is throwaway material. It is a straw or a little pipe or something
Yes.
like that. So, I hope your students will be satisfied. But I have many more experiments left. I could not do them, but I think I should not make much more pressure on them. Then they will be frustrated and go away. So, if you decide to
Thank you so
continue,
much, sir.
if you want to continue
Yeah.
this thing, then we can again come to this webinar and do it. Okay. Thank you very much.
Thank
all,
you so
everybody.
much, sir. It was nothing short of incredibly informative and interesting session. And we, all the children, and I think students, parents, everybody must have enjoyed. So thank you so much, both of you, for being here. The essence of all beautiful art is gratitude. I deem it an honor to propose the vote of thanks on behalf of Father LeBlond School to all those who helped us in making this webinar such a resounding success. I thank our esteemed guests for volunteering their time and experience. We are really enlightened with your knowledge and presence. We are thankful to our Honorable Director Sir and Principal Ma'am for their constant guidance and motivation. A special thanks to our Deputy Directors, Ms. Bias Paul Chaudhary and Mr. Bukul Paul Chaudhary for their continuous support and coordination. My heartfelt thanks to our students, teachers, parents for their active participation, and a special thanks to Proloy Kumar Maiti, my colleague and the physics teacher of Father LeBlond School. It's the audience like you that would make the presentation awesome. Thank you very much for your unwavering attention throughout this presentation. So we wrap up for today, and we will meet again for another round of hands-on learning experience with this stalwarts. Thank you so much. Good evening. Namaskar.
Good evening. Good evening. Everybody may